So this is work with my colleague Paul Shade in the Air Force. Okay, and then, so the convergence study is kind of an abstract thing to do. So I just sort of wanted to sort of offer what our motivation is. So the experiments, we have the Air Force sponsors a beamline at Cornell High Energy Synchrotron Source, where they do a lot of polycrystalline measurements using high energy X-ray diffraction. They put a specimen in the beam, pull it, rotate it around to capture all the diffraction vectors, and then process it to find grain centroids, orientations, and strain tensors. And it can be usually hundreds, if not more, of grains. So now the question is, we want to simulate this. So the thing I was wondering about is because all the grains, you're going to have basically discontinuous coefficients across all the grain interfaces. So the question is, now you can't expect your solution to be more than H1, so how does the lack of regularity affect the convergence of all different things? So now just a number of questions. I just kind of wanted to sort of wondering how everything looked in the process. So do the individual grains, how do they converge? Does every grain converge in the full continuum norm? And then we also have grain average values because we have like the average strain tensor in the thing in the experimental data. So then that's continuous linear functional. So we have linear functionals over every grain that we want to see how they converge. And then also a lot of users are kind of interested in point values, with totally understandably. So so the question is, what does it look like for point values? Do they converge? Do they not converge? And what does it look like? So all those things, and or maybe do you gain anything by using higher order elements? Well, you wouldn't globally, but does that help your grain averages within the thing? So, but even beyond that, it's a good exercise of the code, and then develops post-processing tools, and then it turns out to be good application of our package, or actually package is. So, I didn't intend this to actually be a demo, but sort of at the point I turned it into a demo for our packages, and it's online now, and if you want to go to the Polycrystalline at some point, you just read the README and you get a good idea of how everything works. So the polycrystal package is just material and microstructure. Specifically, single crystal material properties is the material part, and then assignment of grain orientations is the microstructure part. And then by grain orientation, I mean sort of the rotation matrix that matches the crystallographic axes to the spatial framework you're using. And then, so the polycrystal package knows nothing about finite elements, but everything is vectorized so it can be used efficiently. Polycrystalline is really the interface with FEniCS, and it's in charge of handling the mesh, and by material process, I mean things like the boundary conditions and input functions that that go into the problem. Okay, then so the input is kind of parameterized so there's an input from each one of those four groups: material, microstructure, mesh, and material process. Also, it may be called deformation. And by parameterized, think string. There's a string that represents each one of those. It's not exactly a string, but just kind of a dictionary key that could be made into a string. Yeah, so, and actually that model works pretty well for when you have users, when you support users who don't really understand FEniCS. So here so if somebody wants to start some simulations, I can set up the basic infrastructure to get them started, and they can just do things by names and mix and match and run lots of stuff. And then if they need more help, then we take it from there. So that's about it. And I just kind of wanted to see how everything, shakes out. And there we go. Okay, now this slide is sort of my grand plans versus what I actually did. The green is actually what we're going to talk about just for this demo, but sort of these are all the other things I had in mind. You know, as soon as you do something, there's a million things that you think of that you also want to do. So the case we're going to look at is we're going to do a steady state heat transfer problem. We're going to use an orthotropic, thermal material that has different conductivities, 3 different conductivities. The microstructure is going to be Voronoi polyhedra, a Voronoi tessellation, or in fact, there's going to be 5 different microstructures. So if you don't know what Voronoi is, it's if you have a set of seeds, there's a tessellation that we define the grains by which seed they're closer to, and it creates basically polyhedral grain shapes. And so we have 5 different microstructures. Each have 10 random seeds, so 10 grains. And then they're also assigned 10 different random orientations. Yeah, so 5 random microstructures with 10 grains each. Now the deformation, so there's just really one simple deformation. I just want to say it sort of made my brain hurt to think of a really an analytic solution that I want to use for all these. So I just decided to use the finest mesh, and in order to that, and because I'm using the finest mesh as the true solution, I just decided to make it a sequence of like 10 different meshes that we'll solve on. So we'll get a good fit, and hopefully that'll take care of that. And then, so back to the deformation. So it's just a single deformation that we're going to run them all on. It goes 0 on the bottom, 1 on the top, 0 flux on the surfaces, and then basically a simple smooth heat source, And then we're going to process all these. So that'll be 50 simulations, and we're going to process them all to find like the L2 norm of the differences for temperature with the finest mesh, and then also for the flux. And then we'll look at grain average quantities, point values, and so forth. And then the error fitting model, we're just going to do a simple linear fit on the log. Okay, so here's the results for temperature. Okay, on the left is like the continuous grain error. We have two things. M is the slope of the fit, so that'll be like the exponent, h squared or h or whatever. So we have 2. And then for the temperature, it's around 2 also, but quite a bit of for the grain averages, quite a bit of variation. Now the point error at the seed is actually, these are, at the seed points. I just chose all the seed points as the points to evaluate, because they're probably the cleanest points you're going to get. They're like the furthest from any of the boundaries. So it all kind of looks kind of hunky-dory. Just a couple comments here. Is one, it's kind of just interesting to me that the continuous grain error, there was a hard upper limit of 2. Nothing did, but no grain did better than 2, but they pretty much all the grains converged, comparably. And then, so they're plotted by percent of the grain volume, so percent of the body. Now the other thing is if you look at the coefficient, the C, again, for the continuous grain error, it looks like it has sort of an upward slope. And I think that's because the plot above it is plotted doing absolute errors, not relative errors. And usually you would see like the error estimate in terms of a relative error. So I think because they're absolute errors, you're getting sort of a rough slope of 1. And I think that would flatten out if you sort of made them into relative errors. Okay, so at this point, everything looks hunky-dory. Oops, can we go back? Thanks. We skipped the slide. Yeah. Okay, oh, there, the flux. There is no slide. I don't think there is slide. Well, it just showed up. Go up one from the summer. Physics, flux, there. Yeah, okay. So now things get fun here, right? So what's going on? How come like now here? So for the flux, we're doing the L2 norm of the flux, which is comparable to like an H1 semi-norm for the temperature, but we get 0.6 as the power. So where did that come from? And then the other thing is now the grain average. So this is a continuous linear functional. It's like 1.5 or 1.6. And so what's with that? I didn't expect that either. And then of course, now the point values, I didn't really know exactly what to expect, but they went downhill fast, And so the colors, the points are colored by like the R squared value of the logarithmic fit. And so that'll tell you what, percentage of the error is explained by the fit. So most of the points are actually very low. So they're not really even, they're just kind of wandering around. It's hard to argue that they're actually converging in any way. Or even some are negative or, oh, I guess not negative. So then that's the question is what's happening? So the next thing I did is I said, well, what if I run isotropic? Change the material from orthotropic with different coefficients, just make them all the same, and that'll make everything an isotropic material. Everything will be perfect, everything should be good. Well, I didn't put in the slide, but I'll tell you what it was, is that, well, for the temperature, it was again hunky-dory, everything was 2. Grain averages were 2.2, point errors were like 2.4. But for the isotropic for the flux, we got continuous grain error of 1, which is what we would expect. But we also still got the 1.5 for the grain average error, so the linear functional, and the points looked about the same. So at that point, the little voice in my head that had been saying, "Look at the literature and see what it's supposed to be," I finally answered that. And so I looked at it, and there's a few things going on. The full grain, the continuous error, and then the grain average error, which are linear functionals, which can be as much as twice. The continuous grain error. The point errors have like L infinity estimates. But here I kind of like actually seeing actual points. It's more concrete representation to me. And so, I mean, you see some converge, but a lot of them don't. So you might get a reasonable answer, but you can't count on it. So then, so finally, I mean, the result that I found that actually says what's going on is there's a paper which I reference in next that says, if you have like discontinuous materials, and if your mesh matches the grain interfaces perfectly, then you'll get full convergence as if it were actually in H2, even though it's not. So that's what's going wrong, because I used just regular subdivisions. They didn't actually match the mesh. The grain interfaces perfectly. We lost like a half a degree of there. But still, that leaves sort of unanswered. How come when I ran this with isotropic, I got the perfect 1, but for the grain averages, I still only got like 1.5, 1.6. So my explanation for that is, well, you think, well, the grain averages should converge, I mean, yeah, so if the continuous grain are converging full, the grain averages should converge 1 more. But what's happening is that those aren't really, we're not looking at the actual grain average error, because when I calculate the grain average, again, the grain it doesn't match the true grain. So there's an error there, which actually loses the same, like half a degree, so on that. Well, at any rate, well, now it turns out that, and a few other people know for sure, if you use Nepper, then you can solve that problem because it rains, because it, there we go. Yeah, so Napper actually can do that. So sort of that, this is sort of my, my future grand plans. And so I'm going to run this with Napper using that and so forth. And really what I want to do in the end is just sort of find out how much, how big a problem can we run and really trust our results well. Okay, so.
Thank you. One quick questions before the break. Yeah.
Can you comment, would it be possible to also use FFT-based methods? So for example, with Damask or the like, for your problem?
Yeah, I don't really know Damask.
Okay.
Yeah.
Okay. So, but FFT solvers in general? So
FFT. Oh, FFT.
Yeah.
I don't have an answer for that.
Yeah, FFT also have big issues at material interfaces, and you get a lot of.
Oh, sorry.
For sure. Yeah. Okay. Thank you again.